The Biot Savart Law. Soon after Ørsted discovered that a current generated a magnetic field, Biot and Savart did experiments to find the magnitude of the field at a point away from the wire. The magnetic field was perpendicular to both the direction of the current and the direction of the point from the wire. Its magnitude, they found, depended on the size of the current, the distance, and the sign of the angle between an individual wire segment and the point where we were looking to find the magnetic field. The words from the previous page point to the vector cross product, which is uniquely positioned to describe the magnetic field due to a current segment. So let's see what we have here. We're saying a little piece of magnetic field is equal to mu0 over 4 pi. Mu0, of course, is the permeability of free space. We have I, which is the size of the current. We have ds, and that will be the wire segment in the direction of the current. R hat, that'll be a unit vector that points from the wire segment to the point where we're trying to find the magnetic field, and R is just the distance from the wire segment to that point. Let's make comparisons to the electric field calculations that we've done. Similar to the electric field, the equation for the magnetic field falls off as a function of 1 over r squared. Unlike the electric field, the magnetic field is not in line with the radial vector between a current-carrying wire and an arbitrary point. Okay, what do we mean there? Okay, so let's see, we have a charge here, or a whole bunch of them flowing. Okay, the electric field will be in that direction there. So if I want to find the electric field at this point, it's in that direction, the radial direction there. We don't have that for magnetic field. The magnetic field will be perpendicular. So at this point here, it would either be like this into the page or this out of the page. Quite different. And there's no physical meeting to a small isolated segment of the current generating a field. Even though we show that, that's for math purposes. An extended current distribution that is part of a larger complete circuit is required. Pictures and equations are many times better than words, especially in physics. So let's show what we're talking about. The wire here is blue, and we've put a little dimensionality on that so you know it's a wire. Okay, so now that I've shown it to you, we'll just erase my thing there. ds is in the direction of the current flow. That's that little vector there. And the unit vector, r hat, points to P. Here's where we want to find the magnetic field. And you can see how r hat is pointing alongside that radial distance. dB is the magnetic field due to the wire segment ds. And which way is it pointed? Well, you use the right-hand grip rule. And if you put your thumb in this direction, right, and you curl your fingers starting this way, on this side of the wire, it will be into the page, and on this side of the wire, it will be out of the page. Since dB has no real physical meaning, we'll integrate over a current distribution to find the magnetic field at the arbitrary point P. So here's where we put it in differential form, and then all we have to do to find it in vector form, we take the constant out of the integral, mu0 I over 4 pi, and we're left with the integral of ds cross r hat over r squared. Let's use the Biot Savart law to find the magnetic field due to a long straight wire at point P over here. For any segment along the conductor, the magnetic field at point P is into the page. You use your right-hand grip rule anywhere along this wire. Okay, there's your wire, that kind of aqua-colored stuff. Put your thumb in the direction of the current, and the current is going up. Curl your fingers and you find that the magnetic field at any point to the right of it is into the page. So let's erase that. We'll just leave one X up there just to remind us. Now we want to calculate the magnitude of the field. We've already found the direction. That was pretty straightforward. We want to find the magnitude due to all the segments. Let's start with the segment down here, little ds, and let's look at some of the trig here. We're going to call this phi 1, that angle phi 1 between ds and r hat. This distance here from the center of our wire here we're going to call y, This is r. A will be the distance, the perpendicular distance to point P, and then we have theta 1 and theta 2 here. So a lot of labeling there. So let me erase all that now. So please study that and be familiar with what we're going to work with. Evaluate the magnitude of the cross product for any segment ds below the x-axis. So the first thing we'll do is rename ds as dy, because we know we're going to be integrating along the y-axis here. So ds cross r hat is going to be dy cross r hat. And what's a cross product equal to for the magnitude? Well, it's the magnitude of ds, or in this case dy, times the magnitude of the second vector, but what's the magnitude of a unit vector? 1 times the sine of the angle between them. So that's phi. So dy sine phi equals dy sine of pi over 2 minus theta. Okay, can you see how these two are complementary angles? They have to add up to 90 degrees. And the sine of pi over 2 minus theta is equal to the cosine of theta. So what we've done is we've replaced the cross product with dy cosine theta. Okay, so take a breath while I erase this, make some more room, continue doing some geometry. We're going to express r in terms of a and theta. R is going to change depending on where we integrate, which little piece of dy we take. So that's a variable, but it's always going to equal a over cosine theta right here, right? Because if r is the hypotenuse, we have r cosine theta equals a, because a is the side next to the angle. So we just moved it around a little bit. So this is pretty key. So can you see where we're going with this? I'm trying to get a bunch of things in theta. And let me erase again. One more thing to do here. We have y, and y is going to be this piece here, will equal a tangent theta, because tangent theta is opposite, which will be y over a. So therefore y is a tangent theta. And what we're going to do, and just one more erasure on this, what we're going to do is integrate. We'll take like a point there and then keep shrinking the angle, right? We keep changing theta, and then we're going to go over on the other side and keep integrating there. So let's see what theta can range from. We will take, this is our reference point, so if we're at infinity, theta is going to equal what? What will this angle be? We'll call it minus pi over 2, and then we'll slowly integrate down from minus pi over 2 until theta is 0, which is right there. And then we'll continue integrating for the line until we get to what? Pi over 2. So our limits of integration will be negative pi over 2 to 0 for the side below the x-axis, and 0 to pi over 2 for the side above the x-axis. A little bit more math. We have dy on the previous page, but we're expressing everybody in terms of theta, and I've said we wanted to integrate in terms of theta. So we have to get rid of dy. So we know from the previous page, y is equal to a tangent theta. Take the differential of both sides. So the differential of y is just dy. The differential of tan theta will be secant squared theta d theta. And then what do we do now? It's hard working with secant squared theta, but we know that's 1 over cosine squared theta. So let's replace it just like this. So now we have dy. Go back to the previous page where we said ds cross r, right? That's the whole guy we've been working with. We've been trying to replace him with something we can integrate. ds cross r hat was dy cosine theta. Now I have a value of dy in terms of theta, so let's just put that down there. And isn't that cool? Cosine theta in the numerator cancels out with cosine squared theta, or it gets rid of one of them in the denominator. So ds cross r hat is a d theta over cosine theta. And at this time, it'd probably be a good idea to go back a slide and just try and draw this out on your own. And then come back here and do the same thing with this slide. And let's erase all the ink. And when you've done that, please go on to the next slide. Almost done. Now put the cross product magnitude, that's this, into the equation that we started with, the Biot Savart equation. And then what else do we have? We have that 1 over r squared. Well, what was r squared equal to? Pretty sure that was a over cosine theta. So we have to square it. We get this term. And we have another cancellation of a cosine theta. And now our problem has reduced to dB at any point, well, at this point here, due to any point on the line here on the wire, will be mu 0 I over 4 pi a, and here's a, cosine theta d theta. Now we are ready to integrate over the entire line segment. The magnitude dB is represented as a function of theta. So we will integrate from theta 1, here's theta 1, to theta 2. So we'll be integrating dB from theta 1 to theta 2. We put in our expression for dB that took us several slides to get to. Pull the constants out, mu 0 I over 4 pi a. We're integrating now cosine theta d theta. Well, the integral of cosine theta is sine theta. And then we evaluate it between theta 2 and theta 1. So if the line were bigger, this whole thing would be theta 1. And if it went to this side, this would be theta 2. So we now have an expression in terms of theta, and the theta 1 and theta 2 actually determine how long the line is, the long straight wire is, how long the wire is. As we've done before, take a limiting case to see if this result makes sense. If the wire is infinitely long, then theta 1 will equal negative pi over 2. Remember a few slides ago I drew the line out here, and if you had an infinite line, this is going to be pretty close to negative pi over 2. And then the other side would of course be positive pi over 2. We substitute those values in here, and what do we get? We get 2, right? When we evaluate this, we get 1 minus a minus 1, so that gives us 2, and we get the magnetic field at a point P at a distance a from the wire is mu 0 I over 2 pi a. That is consistent, it's the same as the result we obtained in our previous unit for the magnetic field about a long current-carrying wire. Compare this to the electric field at a distance a from an infinitely long wire. We did that certainly during the Gauss's law unit of this course. We have the magnetic field, which we just calculated now, from a long wire, and here is the electric field, again at a distance a. They're very similar. They have a linear dependence on the charge density, all right, for the electric field, and then the current for the magnetic field, and they both decrease as 1 over a, the distance away from the wire. Consider a current-carrying loop of wire of radius a. The loop is oriented so it is centered on the x-axis, which is here, which is pointing out of the page. The current is flowing as indicated. So as we look at it, that's flowing in what? The counterclockwise direction. Find the magnetic field at point P at a distance x, where x is a constant this time, from the center of the loop, and a distance r from every point on the loop. And that's this. So you can see we have a triangle there with x, r, and a. So let's erase all that. We'll be using the Biot Savart law. First we'll talk about what the vector behavior of the magnetic field is at point P, and then we'll go ahead and calculate the magnitude. We'll start by calculating the magnetic field at point P due to a small segment of the loop ds up here. ds is in the direction of the current. Here's Biot Savart again, just to remind you. Now dB will be perpendicular to ds and to the unit vector r, which is drawn between ds and point P. So let's erase up here and show you where the unit vector is. Okay, here's the unit vector, and here's ds. They're perpendicular, and when you take the cross product, which will give you the magnetic field, that has to be perpendicular to both of them. And that's listed right here. So we're going to have to resolve dB into its components. One component will be along the x-axis, we'll call it dBx, and the other one will always be perpendicular to dBx, so we'll call that dB perpendicular. And this is a little tricky to see, but fortunately we have a shortcut here to get rid of him, and then you can see the angle theta here between dB and dBx is the same angle theta. And let me erase again. A lot going on in this picture. We have this angle theta here, part of the triangle which has side A, R, and X. And then you do a little geometry, right? This right here would be 90 minus theta. Then you just go around the angles, and it turns out that this guy will also be theta. So let me erase that and see if you can make that work. And then we'll go to the next slide. When the electric field was calculated due to a charged loop, a symmetry argument was used. There was no perpendicular component of the electric field at point P, as it was canceled out by charge segments that were opposite each other on the ring. So you'd have one segment up here, another one up here. They'd both have electric fields perpendicular. One would be like this, and the other would be like this. So they would all cancel out, and they would reinforce in the x direction. The same symmetry applies here. ds up here is creating a magnetic field in this direction, and its projection perpendicular to the x-axis is here. You use the right-hand thumb rule to get that. If I have a current flowing down here in this direction, using the right-hand thumb rule, we have a magnetic field coming in this direction, and when we take dB perpendicular, it cancels out with this one. So the magnetic field at point P will be solely along the x-axis. It will point from the center of the loop to the right along the x-axis. So it'll be going in that direction. The field lines, right, because these are magnetic field lines, not electric field lines, will go out, come around on the other side, and come back in. We have the direction of the magnetic field from the last slide, and now let's start figuring out the magnitude. Start with the vector cross product, because that's kind of easy. The vector cross product is ds cross r hat. ds is perpendicular to r hat at every point. That's how we set the problem up. So it's going to be the magnitude of ds, which is just ds, times 1. The magnitude of a unit vector is 1, times sine 90. Sine 90 is 1, and the entire cross product reduces to ds. Every single current segment is the same distance from point P. Okay, wherever you are on this ring, your distance r away. And since the radius is a, we do a little Pythagoras, and we find that r is equal to the square root of a squared plus x squared. So let me just show you the triangle again. Here's a, over here is x, and here the hypotenuse is r. So we're going to take those values and put them in to Biot Savart. Here's the substitution. And notice we didn't deal with that on the last page, but that comes out because that's a constant. So we have ds over a squared plus x squared is the magnitude of the magnetic field at point P. But we already said these components cancel out, so all that survives is dBx. And since this angle here is theta, dBx is equal to dB cosine theta. And then what's theta equal to? Well, remember, it's the same angle as this, right? And it came out to be here. So cosine theta is a over the square root of a squared plus x squared, adjacent over hypotenuse. We now have what dBx is, which is also going to be our final magnetic field. And here's where the cosine theta came in. We do a little rearranging, taking out all the constants, putting them in front, and dBx is equal, all of these are constant, okay, times ds. Now we integrate around the loop, we sum up all the little ds's to find the total magnetic field at point P. This is the easiest part of the derivation. The line integral, where you add up all the little ds's around the circle, you just get the circumference of the ring. Symmetry helps in these problems, doesn't it? So here's our dBx. We're going to do this formally. We do the line integral of ds and that's just going to be 2 pi a. Then we move things around to make it pretty, and here's our final expression for the magnetic field at point P, and it is all in the x direction. So if we wanted to do this as a vector, put a little vector hat there, and then put I hat telling you it's along the x direction. Let's plot a graph of the magnetic field along the x-axis. Here's our expression for the magnetic field, and again its direction is in the x-axis. If we want to find where you get a maximum value there, what's the only variable we can change? Well, the current's the same, the radius of the loop is the same, but we can find where along the x-axis we want to find the magnetic field. So if we want that to be a maximum, we want the denominator to be as small as possible. When is it as small as possible? When x is equal to 0. So you plug that in, do the math, and there's our maximum value for the magnetic field. It is right in the middle of the loop of wire. And then it's going to fall off rapidly as a function of x cubed, which is the distance from the center. And where did the x cubed come from? Right here. You have x squared to the 3/2, which is x cubed. So the magnetic field is very strong right in the middle of the loop, then falls off very rapidly. Let's compare the two magnetic field derivations that we've done with Biot Savart. We found that the magnetic field at the center of a current carrying loop of wire, okay, and let's call it radius r, is going to be B is mu 0 I over 2r. The magnetic field at a distance r, okay, see how we're matching the r's up, from a long current carrying wire is mu 0 I over 2 pi r. I don't ask you to memorize a lot of things, but when you're taking an exam and you're running out of time, this would be a handy thing to just know. And I guess one way of knowing it is typically when you have a circle, you should have pi somewhere in the equation. I'm just making that up. There is no pi there, okay? It's just mu 0 I over 2r. When I have a long wire where you wouldn't expect a pi, well, there it is, mu 0 I over 2 pi r. And if you have a better way to remember it, please feel free. This is kind of just how I do it.